Welcome back. In the previous class, we had seen the condition for maximum utilization for a single stage impulse steam turbine, and we have seen that the utilization or the maximum utilization is given by cos square alpha 1 if Cb and K are equal to 1, and we have also seen that epsilon max will be equal to 1 if alpha 1 equals 0 degree, or cos 0 will be equal to 1. So 1 square will be 1, that is the maximum utilization which we can achieve. So that is what we had seen in the previous class. But the major drawback with that is, if you are using a single stage impulse turbine, then the ratio of U by V1, the speed ratio or phi should be half to achieve maximum utilization. So we have seen that epsilon max will be given by this if U by V1, that is phi, the speed ratio is 1 over 2 or 0.5. In that case, what it says that if the blade velocity, the tangential speed of the blade or the tangential velocity of the blade is half of V1, that is the absolute velocity of the steam at the inlet, then we will be able to achieve maximum utilization. Once again, I am repeating that if U is the tangential velocity of the blade is half of the velocity of the absolute velocity of the steam at the inlet, then only we can achieve maximum utilization. If that has to happen, then the velocity of the steam from the nozzle will be very high, because in the case of an impulse turbine, we are converting all the pressure energy into kinetic energy in the nozzle. So generally the pressure inside the boiler will be around 200 bar, and if you convert that to atmospheric pressure, then you have very large amount of energy which will be converted into kinetic energy. So the velocity of the steam coming out of the nozzle will be very high, and as the turbine has to rotate at very high speed, that is one of the drawback. So the tangential speed of the blade should be very high, that leads to lot of stresses. That is one major problem. And the other one is the exit velocity of the steam will also be high. V2 is the exit velocity, and we have seen that while defining the utilization factor, we have seen that it is energy, the Euler's energy equation divided by Euler's energy equation plus losses, where losses was V2 square by 2, that is the kinetic energy carried by the steam when it is moving out of the turbine. In that case, we call that energy as the loss of energy as carryover losses. Since V2 is very high, the carryover losses will also be very high. So we will be losing a lot of kinetic energy which could have been utilized if we have more number of moving blades. So what we do is, to overcome the drawback of very high speed, if you are using a single stage, then U should be half of V1, that is the tangential speed of the rotor should be half of V1. If the tangential speed is more, then the rotational speed, that is the RPM of the turbine will also be very high, and that induces lot of mechanical stresses on the rotor and the blade, which will lead to the failure of the turbine over a very short duration of time, and also to prevent or to reduce the carryover losses. Our aim to the maximization of epsilon max, if you remember module 2 in the general analysis, to maximize utilization factor, we had reduced V2. So we had made V2 axial when we are dealing with axial flow turbines. So we had made V2 axial so that it will have a very minimum value. So we need to reduce the carryover losses. One agenda for us is to reduce carryover losses, and the other one is to reduce the speed of the turbine. So these two is achieved with the help of compounding. Compounding is nothing but using 2 or more rows of moving blade on a same shaft. So if you have 2 or more rows of moving blade, then the energy absorbed by the moving blade can be distributed over those 2 or more rows of moving blades, which reduces the speed of the blades and also reduces the carryover losses. So this is the need for compounding in an impulse steam turbine. For a reaction turbine we don't use compounding. For an impulse steam turbine we go for compounding, and compounding can be done in three ways. The first one is the velocity compounding, the second one is the pressure compounding, and the third one is the combination of these two, that is velocity pressure compounding. So we will go through each of them. First let us see what is velocity compounding. So here I have the nozzle, then I have the moving blade. So this nozzle and moving blade, one set of nozzle and moving blade constitutes one stage. So whenever we talk about stages, multiple stages, then always it is a combination of a fixed blade and a moving blade. So in this case the first one will be the nozzle and the first row of moving blade. So this will be one stage. Then you have the fixed blade and you have the moving blade. So the combination of these two will be the second stage. So here I have shown two-stage velocity compounded turbine. Again this is impulse turbine. So energy exchange happens in the moving blade, the energy which is in the form of kinetic energy only. So only the kinetic energy will be absorbed by the moving blade, and you can see that the blades are symmetric. So if I cut this blade here, then the blade is symmetric over the central axis. So these are the blades where only kinetic energy of the fluid will be observed. Okay. Now the steam comes out of the boiler and enters the nozzle. So in the nozzle the pressure energy will be converted into kinetic energy. Now we have the moving blade where the first row of moving blade absorbs a part of the kinetic energy. So in the single stage whatever kinetic energy has to be absorbed, so all has to be absorbed by the only one row of moving blade. But here we have multiple rows of moving blade. So the first row of moving blade absorbs a part of the kinetic energy. Then we have the fixed blade. This is just to guide the steam to the next row of moving blade. So there is no change in pressure or velocity when the fluid passes over the fixed blade. Again here, since there is no change in pressure, the fixed blades are also symmetric in structure. So there is no changes in the shape of the moving blade. So it is symmetric over the central axis, and since these blades are fixed, there is no motion of the blade, and since there is no movement of the blade, there is no work done. So the blades will not absorb any energy. So the steam will exert certain amount of force on the blade. The blade will also exert equal amount of force on the steam. So there is no energy exchange in the fixed blade. Then we have the moving blade. Again the remaining kinetic energy will be absorbed by the second row of moving blade. So here I have only two stages. You can have multiple stages depending on the energy available and the speed of the turbine required. Okay, now let us see what happens to the pressure and velocity of the fluid or the steam. Now the steam is coming out of the boiler at a boiler pressure which is very high, and as it passes through the nozzle, its pressure gets reduced or gets converted into kinetic energy. So the pressure reduces, at the same time the velocity increases. So the velocity is increasing while the pressure is reducing. And since we are dealing with impulse turbine and this is velocity compounding, all the blades, that is the moving blade, fixed blade and the moving blade, so the two rows of moving blades and the fixed blade in between them are symmetric in structure, that is the inlet angle and the outlet angle are same. So there will be no change in pressure, and because of that the pressure remains same throughout the blade. So this will be the exit pressure. So the pressure remains same as the steam passes through the moving blade, fixed blade and the next row of moving blade. Now let us see how the kinetic energy will be absorbed, which in turn how the velocity reduces. So as the steam passes in the gap between the nozzle and the moving blade, there is no change in velocity, and as the steam passes through the first row of moving blade, it loses certain amount of kinetic energy. And then it passes over the fixed blade where there is no change in the kinetic energy because the blades are fixed, they are not moving, so they will not absorb any energy. So since they are fixed, there is no motion, there is no work done, so the kinetic energy remains same as the steam passes over the fixed blade. The purpose of the fixed blade here is to redirect the steam towards the next row of moving blades. So now the steam is passing over the next row of moving blade, the second row of moving blade. So here there will be certain amount of energy absorbed. So the kinetic energy will be absorbed by the moving blade. So the velocity reduces and then comes out with the exit velocity. So this exit velocity squared by 2 will be our carryover losses. If we had only one stage, then this would have been the exit velocity. So we would have lost a larger amount of energy if you are using a single stage of turbine. Since we are using 2 rows of moving blades here, or we are using 2-stage turbine here, we are utilizing more amount of energy when compared to the single stage. And use of 2 stages, the energy absorption will be distributed, and because of that the speed of the turbine can also be reduced. So for this, the example is Curtis turbine. Curtis turbine is a 2-stage impulse steam turbine which is velocity compounded turbine. So to be clear, in the case of compounding, we are using 2 or more rows of moving blades so that the energy absorption can occur in more than one row of moving blade, which reduces the speed of the turbine and also it reduces the carryover losses. So here we have seen that in a velocity compounded steam turbine, the steam enters the nozzle with boiler pressure, and then in the nozzle all the pressure energy will be converted into kinetic energy. So the pressure reduces to exit pressure or the atmospheric pressure, and the velocity increases to its maximum value. And as the steam passes over the first row of moving blade, a certain amount of kinetic energy will be absorbed by the moving blade, so the velocity reduces, and then the steam enters the fixed blade where there is no work done because the blades are fixed, they are not moving. So since there is no displacement of the blade, there is no energy exchange in the case of fixed blade. The fixed blades are also symmetric in nature, so there will be no change in pressure or velocity. So since it is symmetric in nature, there is no change in pressure. Since it is fixed, there is no motion, the velocity also remains same. And as the steam enters the next row of moving blade, so here the moving blades absorb certain amount of kinetic energy, so the velocity reduces, but since the blades are symmetric in nature, the pressure remains constant. Then the steam comes out with the exit velocity, which is much lower than the exit velocity of the single stage or the first stage of the steam turbine. So thereby reducing the carryover losses. Okay. Now let us see the working of a pressure compounding or pressure compounded impulse steam turbine. As the name indicates here, it is velocity compounding. So the velocity or the kinetic energy will be absorbed in stages. This is a pressure compounding. So here the pressure energy will be utilized in multiple stages. So here we have the nozzle, then we have the moving blades. So the moving blades for the first and the second stage are symmetric because this is an impulse turbine. So there is no change in the pressure as the steam passes through the moving blade. But if you observe the fixed blade here, it has aerofoil in shape. So the shape of the moving fixed blade is aerofoil. So which means to say that here this also acts as a nozzle, and there will be change in pressure as the steam passes over the fixed blade. Since the blades are fixed, the blades are not absorbing any energy, so the change in pressure results in increase in the kinetic energy of the steam. So now let us see the working of this. So here we have the steam entering the nozzle at boiler pressure, and as it passes over the nozzle or as it passes through the nozzle, certain amount of pressure energy will be converted into kinetic energy. Okay, so the reduction in the pressure energy leads to increase in the kinetic energy of the steam, and then the steam enters the moving blade. As it enters the moving blade, here the pressure remains same or constant because we have symmetric blades, and since there is no change in the passage area, the pressure remains constant. So here the pressure remains constant, but these are moving blades which are absorbing certain amount of energy from the steam. So because of that, the kinetic energy reduces, or the velocity of the steam reduces, and now the steam enters the fixed blade. If you see the shape of the fixed blade, so here the shape of the fixed blade was symmetric, but here we have aerofoil blades. Because of the aerofoil shape, so the pressure reduces, and pressure reduces here, and the pressure energy will be converted into kinetic energy, so the velocity increases. So the velocity increases and the pressure reduces. Now the steam enters the moving blade. So here we have a symmetric blade, so there is no change in pressure, the pressure remains constant, and the pressure comes out with exit pressure. Now as the steam passes over the moving blade absorbs kinetic energy, and the velocity of the steam reduces and comes out with exit velocity. So exit velocity squared by 2 will give us the carryover losses. Here also we can see that the steam is coming out of the turbine with a low velocity, which means to say that we have reduced the carryover losses. This combination is nothing but you are using two single stage impulse turbine, one after the other, which are operating at different pressures. So this stage is operating at higher pressure, this stage is operating at lower pressure. They are similar to two simple impulse turbine placed one next to the other. So here this is one way of compounding, and this is another way of compounding. Then we have the combination of two, which we will see now. The next method of compounding is pressure velocity compounding, or this is similar to two velocity compounded turbines placed one next to the other, where the pressure energy will be partially utilized by the first stage, first set, and partially utilized by the second set. So here in this case we have the nozzle, where a part of the pressure energy will be converted into kinetic energy. So the velocity increases, and then the steam enters the moving blade. So here a part of the kinetic energy will be utilized, and then we have the fixed blade. If you observe the fixed blade here, it is asymmetric in structure. So there is no change in pressure energy as well as kinetic energy as the steam passes through this fixed blade. Then we have the moving blade, where the remaining kinetic energy will be absorbed. So if you remember, here I said a part of the pressure energy will be converted into kinetic energy. So as the steam passes through these three rows of blades, the first row of moving blade, fixed blade, and the second row of moving blade, the pressure of the steam remains relatively high. And then if you observe the next row of fixed blade, so here the shape of the blade is aerofoil in structure, which means to say that here the pressure changes, and since it is a fixed blade, the change in pressure or the reduction in pressure will be converted into kinetic energy. So since the blade is not moving, the kinetic energy will not be absorbed in the fixed blade, but in the case of reaction turbine, the moving blade will be in the form of aerofoil structure. So the cross section will be aerofoil in structure. In that case, since the blade is moving, whatever the changes in the pressure energy will be absorbed by the moving blade. But here, since we have a fixed blade, the pressure energy will be converted into kinetic energy as the steam passes through the fixed blade. So if you remember this entire stage from here, the nozzle, first row of moving blade, fixed blade, and the second row of moving blade is similar to a velocity compounded steam turbine. Then this fixed blade, which is aerofoil in shape, acts as nozzle for the second stage of velocity compounded steam turbine, where we have the moving blade, which is symmetric in structure, so it's an impulse turbine and absorbs a part of kinetic energy. Then we have the fixed blade, which is similar to this, which is symmetric in structure, and because of that there is no change in pressure or kinetic energy. Since the flow area remains same, pressure energy remains same. Since the blade is fixed, kinetic energy remains same. And then the steam enters the last stage, where the steam, the kinetic energy of the steam will be converted into mechanical energy, or the kinetic energy will be absorbed by the moving blades. So as the steam passes through this blade, the fixed blade, which are aerofoil in shape, the pressure changes and the pressure attains the atmospheric pressure or a lower pressure, and the pressure remains same as it moves through the third row of moving blade, fixed blade, and the fourth row of moving blade. Okay. Now let us see the variation of pressure and velocity in different stages. So first, the pressure partially gets converted into kinetic energy. So the kinetic energy increases. Now the steam passes over the moving blade. It's an impulse stage. So in the moving blade, only the kinetic energy is absorbed, the pressure energy remains same, because the blade is symmetric in structure. So you need to remember, if you see a symmetric structured blade, then there is no change in pressure energy. So the pressure remains same, but a part of the kinetic energy will be absorbed by the moving blade. So the velocity reduces. Now the steam enters the fixed blade, which is also symmetric in structure, so there is no change in pressure, so the pressure remains same here. Now since the blade is fixed, there is no change in kinetic energy also, because there is no change in pressure, so the energy will not be converted into kinetic energy, and since the blade is not moving, it's fixed, the velocity also remains constant. There will be few losses due to fluid friction, but that we will not consider here. So the energy and the pressure will remain same as it passes through the fixed blade. Then we have the moving blade, where if you observe the moving blade, it is symmetric over the central axis, and because of that the pressure remains constant. So the pressure remains constant as it passes through the moving blade. But the moving blade absorbs kinetic energy, and because of that the velocity of the steam reduces and reaches its minimum value. Now it passes through the next row of fixed blade, which are aerofoil in shape. So here the pressure energy gets converted into kinetic energy. So relatively high pressure which is entering this fixed blade will lose its pressure energy, and the pressure energy will be converted into kinetic energy. So the velocity again increases. The velocity of the steam increases to its original velocity when it was coming out of the nozzle. Now the steam passes through the moving blade. So moving blade is symmetric in structure, beta 1 and beta 2 are same. So because of that there is no change in pressure energy, so the pressure remains constant, but the blade absorbs certain amount of energy, certain kinetic energy from the steam. So because of that the velocity reduces. Now the steam enters the fixed blade. Fixed blade here it is symmetric, similar to the second row of fixed blade. So because of that there will be no change in the pressure and kinetic energy or the velocity. So the velocity remains constant and the pressure also remains constant. Now the steam enters or passes through the last row of moving blade. So here the blade is symmetric, so there is no change in pressure energy. So the pressure comes out of this stage with pressure equal to exit pressure, but since the blades are moving, it absorbs certain amount of kinetic energy. So whatever the remaining kinetic energy, that will be absorbed by the moving blade. So it comes out with exit velocity. So here this is a combination of two velocity compounded turbines which are placed one next to the other, and the pressure energy will be partially absorbed in the first stage, and then the remaining pressure energy will be absorbed in the second stage of the velocity compounded turbine. So that is why the name pressure velocity compounding. So we are combining two velocity compounding with a pressure compounding. Okay. So this is the working of a pressure velocity compounding, and here the exit velocity is very less. Because of that, carryover losses will also be very less, and since we are using 4 stages here, energy will be equally absorbed by all the 4 stages. So the velocity of the steam turbine can be reduced, and that will be in a manageable range. So because of that, this kind of arrangements are used. So once again, here the steam enters the nozzle at the boiler pressure, which is very high, around 250 to 300 bar, and here in the nozzle a part of the pressure energy will be converted into kinetic energy. So the pressure partially reduces and the velocity increases, and as it moves, as the steam passes through the moving blade, so here a part of the kinetic energy will be absorbed, but since the blades are symmetric, the pressure remains constant. So there is no change in the flow area, so the pressure remains same. Because of that, the pressure energy remains same. And then the steam enters the fixed blade. Again here the blades are symmetric in structure, so there is no change in pressure, and since the blades are fixed, the blades are not absorbing any energy, so the kinetic energy or the velocity also remains constant. Then the steam enters the moving blade. So this fixed blade is just to redirect the steam coming in this direction towards the next row of moving blades. So the steam enters the next row of moving blade where the remaining kinetic energy will be absorbed, so the velocity reduces, but since the blades are symmetric, the pressure remains constant. Then the steam enters the next row of fixed blades where the shape of the blades are aerofoil in structure. There is a change in the flow area, and because of that, so the blades, fixed blades here, which are aerofoil in shape, acts as a convergent divergent nozzle. So because of that, the pressure energy will be converted into kinetic energy. So the pressure reduces to exit pressure and the velocity increases. So with this increased velocity, the steam enters the next row of moving blade, which is symmetric in structure, so the pressure remains constant, but since the blade is moving, it absorbs the kinetic energy and the velocity of the steam reduces. Then it enters the fixed blade, which is symmetric in structure. So since we have the symmetric blades here, there is no change in the pressure and kinetic energy. So the pressure and velocity remains same. Then the steam enters the moving blade. Again the moving blades are symmetric in structure. Because of that, the pressure remains constant, but the blade is moving and it is absorbing kinetic energy. So the velocity of the steam reduces, and the steam comes out with a very low exit velocity, reducing the carryover losses. So this is the need and the methods of compounding. So we have seen that the steam enters the nozzle, the steam comes out of the nozzle with very high velocity, and to have maximum utilization, we need to have the speed ratio, that is the tangential speed of the blade divided by the absolute velocity at the inlet should be 1/2, or the tangential speed of the blade should be half of the absolute velocity at the inlet, which is very high. So the turbine has to rotate at very high speed to have maximum utilization when you have only one stage. And since the turbine we have only one stage and the steam is entering at very high speed, the steam will also leave the turbine with very high speed, so that also increases the carryover losses which could have been utilized by the turbine. So because of that, because of these two reasons, to reduce the speed and to utilize maximum amount of energy, we go for compounding, where we use 2 or more rows of moving blades instead of just 1 row of moving blade. And in compounding, we have 3 methods of compounding or adding moving blades to the turbine. The first one is velocity compounding, where in the nozzle the pressure energy will be converted into, all the pressure energy will be converted into kinetic energy, and the increase in the velocity or the kinetic energy will be absorbed by multiple rows of moving blades. Then we have the pressure compounding, where the pressure energy will be partially converted in each stage, and then the change in the kinetic energy or the increase in the kinetic energy will be utilized by the next row of moving blade. Then we have pressure velocity compounding, which is a combination of velocity compounding and pressure compounding. So from here till here it is a velocity compounded stage, and from here till here it is a velocity compounded stage, and the pressure energy is being utilized between these two stages. So we are pressure compounding 2 velocity compounded stages, and that we call it as pressure velocity compounding. So these are the 3 methods by which we can have compounding in an impulse steam turbine. Remember, compounding is used only for impulse steam turbine and not for reaction turbines. So now in the later classes we will see the analysis of 2-stage impulse turbines. It can be velocity compounded, pressure compounded. So we will see in our syllabus we will see 2-stage impulse steam turbine, and we will solve problems on that.